and I'm on the y-axis from 0 to 3. And now I'm going to get my differential amount of charge here, dq, which is just the charge density, rho L, times dy, times dy, pardon me. Does this make sense to everybody? Now it's going to be at a position y. This is going to be at a distance y away from the origin. And if you look here, if we want the electric field at this point, well, I'm going to even move this, try to expand a little on this. If this is at a differential point y, and this is going to be 1, 2, if this is the 3 down here in the x direction, and we want the electric field, we start with the differential electric field here. So the differential electric field generally is dq over 4 pi epsilon naught. Then it's divided by r squared, and it's times ar. I've already got what dq is. It's rho L dy. Y'all follow me on that one, class? Now we need to get r. So when we get r is this vector from here to this position right here. Y'all follow me? So r is going to have, if you look at this, it doesn't have a z coordinate in this case. R in this case is going to be what? Well, it's going to be, it's really going to be, in terms of x, it's just going to be 3x, or 3ax, pardon me. You see how that's always going to be 3? Y'all follow me? It's 1, 2, 3. In the x direction, no matter where you are on this line, you're only going 3 in the x direction. Y'all follow me, class? Can y'all see that? Next, it's going to have, we have to get the y coordinate change. You always go from the point of observation minus the source point of the electric field, and you subtract them. So here, the point of observation is at x equals 0, isn't it, class? And here, the point of observation is going to, or at y equals 0, pardon me. Here it's y, so this is going to be minus y ay. I hope you can appreciate the way I'm doing this, and there is no z difference. What I really should have said is to get r, you take these coordinate points for the field point of observation, and subtract the coordinates from those of the source of that electric field, the charge. Y'all with me? So here it's really just 3 in the x direction, minus 0 all the time. So it's 3ax, and then it's going to be 0, that's the y coordinate at this point, minus y. Everybody follow me? If you do, raise your hands. I want to make sure you see it. You all see it? Okay. That's r. Now we need r magnitude, and that's just going to be the square root of 3 squared plus y squared. Everybody follow me on that one? This is actually a pretty good problem. After that, we need ar. How do we get ar, class? R vector over magnitude of r, correct? Isn't that right? I'm not even going to put it there, but you can all see it's just this over that. Now the reason I'm not going to is I'm going to go right for this thing. I'm going to assemble it, then do the integration, okay? All right. So I come over here, and therefore I say the differential electric field will be equal to dq, which is rho L dy, over 4 pi epsilon naught. Now I have r squared, that's this squared, 3 squared plus y squared, right? Now it's times ar, which is going to be on top, 3ax minus y ay. And on the bottom, it's just this, so I can make this to the 3/2 power. Please take a look at that and make sure you understand the step, especially the last step, where when I put ar in there, I had the vector 3ax minus y on top, and then I just took the magnitude and I lumped it into that already existing 3 squared plus y squared term. Y'all follow me, everyone? How many do? Okay? Now, that's the differential. To get the total electric field, the only thing I do is take this and integrate it from y equals 0 to 3. Everybody with me? Bless you. Okay? Now, if you're going to do that integral, I suggest this. Take a look at what really is going to change. Well, for the first part, I have rho L dy 4 pi epsilon naught 3 squared plus y squared to the 3/2 power. I'm integrating this portion dy, so my real integration that I need, well, let me do it here. Is, and I'll call that EX. The X component will be equal to rho L over 4 pi epsilon naught. Then I have a 3 here, I can take out in front. And then I have the integral from 0 to 3 of dy over 3 squared plus y squared to the 3/2 power. You all agree with that? And this integral is of the form right here. If you have dx over x squared plus a squared to the 3/2 power, and you integrate that, you end up getting x over, that would be a squared times x squared plus a squared to the 1/2 power. And this is in the back of the book, I believe. You can check me on that one. But this is one of those integrations you don't have to memorize. If you're worried about, well, I won't know this on an exam or something, I'm not going to give you any kind of tricky integrals. All right? And the only way to really get used or know these things is just use them. You have to be exposed over and over again, because I think this one, I think you use a trigonometric substitution, a tangent substitution to do it, but I don't expect you to remember that. And you can look in your book. They have them in the back of the book, and there's integral tables all over. You can take a look. I don't know what pages. So that's the first part. That means this one is what? Let's see. My a squared is really going to be equal to, so this is going to be EX is equal to rho L times, this is rho L, pardon, times 3 over 4 pi epsilon naught here. And then you're going to have, this becomes y over 3 squared plus y squared to the 3/2. And it's evaluated from 0 to 3. Well, when y is 0, the first term goes to 0, right? And then when y, y is 0 goes away. And when y is 3, it would be this. See, I've got to evaluate this part right here, but when y is 0, that term goes away, so I just worry about that. So I'm just going to replace that when this is 3 here, and this becomes 3 here. That would be the EX component. Y'all follow me? I'm just evaluating the integration. Now, I'm going to simplify it. Y'all see how I got 3 squared on top and the bottom? Right? I'm going to get rid of that 3 squared. It's 3 times 3 over 3 squared, so just get rid of that. Y'all follow me what I'm doing here? Just trying to clean it up a little. So I get rid of this. Now, this is really 9 and 9 is 18, right? So I can just put 18 to the 3/2. And then rho L is 10 nanocoulombs. If you want to put them there, that's 10 to the minus 8. And 4 pi epsilon naught 1 over that is really just what? 9 times 10 to the 9th, isn't it? 1 over 4 pi epsilon naught. Remember that constant k? Like epsilon naught is what? 1 over 36 pi times 10 to the minus 9th, right? Try it. I think this will be a little easier. This is going to be times 9 times 10 to the 9, or 10 to the 9. And so this should be the x component. Can you tell me what this is, by the way? Well, 10 to the minus 8th times 10 to the 9th is 10, so that's 90 on top. It's 90 divided by 18 to the 3/2 power. Anybody? Yeah.
Would that be 18 to the 3/2 or 18 to the
1/2, sorry, 1/2. You're absolutely right, that's on me. 1/2 power. From there, yeah. Yeah, from that. My bad. What does it come down to? I want to see it. We'll do the second integration. It's just the integral that drives people nuts sometimes.
21.2.
21.2.
Is that what they have? For the x component. 21.2?
Yeah.
Yeah, they have 21.
That's the x component. Now we need the other component, right? I just want to make mention of this. You all follow what I'm doing here? The integration gets a little irritating. Just level with you, all right? You have symbolic integrations and all that. If you want to look online for something, Wolfram Alpha has something that does symbolic. You can look, there's tons of tables, and I think your calculators, how many have symbolic integration on your calculators? See, I mean, it's all over the place, so you can figure out the answer to these integrals. If you want to, you can do the trig substitution. I mean, if you want to get old school and do that just for kicks, sure. All right, now the next part is this part right here, the last part. Now, what do you notice about this? This is the easier integral, right? Because it's of the form y over 3 squared plus y squared to the 3/2. So I'm going to erase this and just do this one over here. So for that one, we would say E, and this would be in the y direction, would be equal to rho L over 4 pi epsilon naught. And then I have an integration of minus y over 3 squared plus y squared to the 3/2 power dy. I don't think I missed anything, and that's going from 0 to 3. Right? Now, then what's the nice thing about this? You got a y up top, right? You got y dy. So, just a suggestion, and it's up to you, right? But if you don't want to mess with tables, just make u equal to 3 squared plus y squared, and then du would be equal to 2y dy. Y'all follow me on this? Now you know why I did that, didn't I? Because I'm going to do substitution and integration, yeah? All right, so look, the only thing I care about is this part of the integral. My ey, therefore, would be equal to rho L over 4 pi epsilon naught. Now, just take a look at this. Y dy, right on top, that's du over 2, isn't it? See how I have y dy there? Everybody? So, I'll put the minus sign out in front of this if it makes you feel a little better. So, and I'll circle it too. So this is going to be du, and then I have u to the 3/2 power. Now that kind of integral I like, right? because that integration is really u to the minus 3/2. And when you do an integration, what's that gonna be? Oh, I didn't put the limits on. Remember, now my limits are not gonna be y, they're u. So when y is 0, the lower limit is gonna be 3 squared. You all follow me? Take a look. I got this right here, correct? All right, so when y is 0, that would be the lower limit. This would still be 3 squared. This would be u equals 3 squared. And the upper limit, when y is 3, this is going to become 3 squared plus 3 squared, or 2 times 3 squared. So what's this going to be? That means ey itself is going to be minus rho L 4 pi epsilon naught. I almost feel like reversing the order on these. What happens when I integrate u to the minus 3/2 du? I get 1 over 1 plus minus 3/2, right? And then I get u to the minus 1/2. Don't I, class? Right? Remember, integration you have to take and goes downstairs there. So what is that going to be? Well, this is really 2/2. Minus 3/2 is minus 1/2, correct, class? So this is minus 2, correct? And that means what? Well, I've got a minus there already. And when I do the integration, it's a minus. I can get rid of this minus here, and it becomes times 2. And then it's going to be u to the 1/2, 1 over, it's going to be this actually. 1 over the square root of 2 times 3 squared minus 1 over the square root of 3 squared, or really 1 over 3. So can you tell me what that is? I can't. It's negative, but it's really 1 over the square root of 2 minus 1 times 1/3. But can you just tell me what this comes out to for E1? Anyone? It's going to be negative, but I can't tell what it is. Can you all read it okay?
What happened to the 1/2 on the DU?
Wait a second. Help me out here. Where are you looking?
Where you did your substitution, your DU over 2 equals y dy. Where did the over 2 go to? Left. Yeah, when you substituted u back in for, like, substituted du in for dy.
Yeah, this should be du over 2. I guess it didn't appear. That's what happened. I'm running through this a little too quick. So this should be here, right? So the 2's would cancel. My bad. Thank you very much for catching that. These 2's will cancel. Anyway, can you just tell me what that is? Rho L, I really don't want to keep playing with this. Was just turning the crank on this problem. I think it's something a little new. Rho L is 10 to the minus 8, 1 over 4 pi epsilon naught is really 9 times 10 to the 9. Right? So it's 10 to the minus 8 times 9 times 10 to the 9th. And then it's going to be times divided by 3. And then it's going to be times 1 over the square root of 2 minus 1. Whatever that is, and I can't tell you. Negative 8.77? Is that what you said? Minus 8.77 volts per meter. Is that what the answer is?
Negative 8.8.
I hope I answered your question.
Yeah.
If the integrations, how many tried that one? Okay, I'm going to encourage you to try them. You may not like the integrations, but if possible, struggle through that. It'll help you in the long run, and you won't forget. Irritating integrations you usually remember a long time because they irritate you. Anyway, I want to just do now, is there another question before I continue? That's actually a good problem, really good problem. And if I would give you a problem like that on a quiz, I would provide integrations, so you won't. I mean, it's-
On exams and stuff, would we be able to use our calculators that would have like the symbolic integration?
Yeah, yeah, I mean, if you use your calculators, I assume that you're gonna use symbolic integration. It doesn't bother me. It's like I'll provide you with the integration if you want me to, but. All right. So, any other questions? All right, let me recap something for you. I want to show you some things that are insights I have on a lot of this stuff that will help you in the long run. So we were talking about that ring. Please write this down too, because this is, I think, valuable. Remember, we start with X, Y, Z coordinates, and we try to get things that are concentric with one of the coordinate systems. This is a loop, and this is a classic problem, or a ring. They have something like this, right? And this loop has a radius of A, and you want the electric field at a distance Z above here, right? And the loop has a charge density rho L on it. So this is just a ring of charge, where the charge exists here, it doesn't vary in magnitude, and here's your ring of charge. Now, last time I said, if you take any differential chunk, and you don't need to write this down, this is an R vector, you get a differential electric field here, and I said by argument of reason, you can come through here and you can find a conjugate point such that the electric field will have the same magnitude for the same differential length, and the horizontal components will cancel and the vertical components will add together. Do y'all remember that? Now, I want you to think about this. If I took all the charge on that loop and I put them at a single point like this, so this is going to be the total charge on that loop, Q. And Q here would be equal to the circumference of the loop times the charge, line charge density, right? Think about it. Rho L is coulombs per meter, 2 pi A would be the perimeter of the loop, or the circumference. Do y'all agree with that? That's all the charge, isn't it, class? All right, now follow me. I'm gonna put all that right here. Then I'm gonna come over a distance A. I'm coming over this radial distance. Then I'm gonna go up a distance Z. And I'm gonna just find out what the magnitude of the electric field is here. Now, I think some of you are gonna figure this out. Y'all with me on this one? So what's the magnitude of the electric field? I'm not gonna ask for the actual direction at all. Well, the magnitude of the electric field will always be the total charge Q over 4 pi epsilon naught, right? Divided by this distance R squared. You all agree? That would be the electric field magnitude, right? Now, intuitively, if that's the electric field, total electric field, I just want this component, the vertical component right there, I know I'm gonna do what? I'm gonna have some kind of a trig function multiplying it, right? And that trig function would be what? Well, it would be, in this case, for this angle at least, it would be the opposite over, it would be actually the sine, right? Y'all follow me on that? Because as the sine goes to 0, it goes to 0, there'd be none. So it would be multiplying this would be the opposite Z over the magnitude of R, or you could just say magnitude of R here. And if I go ahead and just expand that, this would all be in the Z direction, because I know the R's, or the horizontal components, cancel out. So I can put an AZ here, And now what you see is I can put the total charge Q, which is 2 pi, A, rho L here. I divide it by 4 pi epsilon naught. And now I have really R cubed and times Z. And this is in the AZ direction. Now, I'm just showing you the way I always remember these things, because people always worry about how can you remember these things. I just take all the charge and I put it at a point, and then I take the vertical component of that electric field, the resulting electric field. Now, I know sometimes people will wonder, well, is it A times Z or Z squared and stuff? But this way you won't mess that up. Right? You find the total charge divided by 4 pi epsilon naught and R squared, that gives you the magnitude. Then just take the projection of that E field on the Z axis. And intuitively, you'll know if it makes sense, because if this was A over R, it would make no sense, because that says when Z is 0, you would have an electric field in the Z direction. That makes no sense. You all follow me? When Z is 0, there ain't no electric field going up or down. There ain't no electric field at all. Right at the origin, it's 0. Do y'all follow me? And sure enough, that formula will show it's 0. Another thing about this, when I go below for Z negative, below the actual plane, the XY plane, it changes directions, and in fact, the electric field does change directions. It'll point in the opposite direction. Now that's how I remember that. But you may not. All right, now I'm going to do the classic problem, the infinite line. This is the ones physics teachers spend a lot of time doing all these canonical shapes. At least they used to when I was young. And it's beneficial to know some of them, but you don't have to know everyone. You can always get there if you need to. So, the next classic problem is this. We're going to take the z-axis as such, and we're going to assume the z-axis has a line charge density rho L. It exists up and down the z-axis. This is the classic one. If it didn't, we would do the same thing we did just a moment ago with the finite length integral, right? And we define the limits. But here, we're going to say it exists forever. And I'm going to come out at distance rho. That will be a constant. And I want to know the electric field at this point. So I want the electric field at this point. And that's only got really, it doesn't matter, phi doesn't matter in this one because the electric field's pointing away from the z-axis at all times, right? You're not going to have to worry about a phi. We could talk about AZ if this thing was finite, but really the electric field only point radially outward at this point. The actual point right here is going to be that rho here has some value. Rho, phi doesn't matter, you can make it 0, and z is going to be 0 in my case. So it's just that far away. Rho can be a constant there. I want that electric field. So I start with a differential chunk right here of charge, and I say that that dq right here is rho L dz. Y'all follow me on that? Next, I go ahead and I draw from this thing a straight line to this point, and this is my R vector, right? And now I can say that the differential electric field pointing in this direction can be defined based on the coordinates I've given you. And I can say the differential electric field will be equal to that charge, dq, or just, I might as well put it down, rho L dz. It's divided by 4 pi epsilon naught. Now I divide it by r squared. So I didn't put down what r is. But just looking at this, what is r? Well, remember you take the coordinates, the point of observation of the E field, minus the coordinates of the source of the electric field. All right, start with rho. Well, the rho coordinate there is rho, right? And minus 0, because you're on the z-axis, a rho, correct? Now here, phi doesn't matter. You're on the z-axis. Phi loses its meaning. Think about it. Phi has what to do? It has what? Has to do with where you are somewhere at a constant row away. There ain't no row away, so there ain't no phi to worry about. You can make it 0 for all I care. Next one, finally, is gonna be the z coordinate. All right, z coordinate of the point of observation is 0, right? I made it that way. Minus this z coordinate, which is z, so it's gonna be minus z a z. And that makes sense. The unit vector's pointing that direction. It's pointing outward and downward. Y'all with me? Now we need magnitude of r, which is going to be equal to simply square root of rho squared plus z squared. And then we're going to need unit vector AR, which is r vector over magnitude of r. Agreed? All right. Now I set up the integration. Well, now I've got to put the r in here. So I have rho squared plus z squared to the just the 1 power times the actual rate, the r vector, which is going to be rho a rho minus z a z, and it will make this to the 3/2 power. Y'all agree with that? That extra half comes from the unit vector. Okay? Making sure everybody's on topic here. Everybody can see. And if I'm going a little too fast, just mention it to me, I'll slow down. Everybody got this? Okay. Now, we still need to get the total electric field, so the way we do it is integrate. And that means the only thing I do is this. Right? And I integrate over the limits. I made this infinite. Y'all understand if it's not infinite, you would put the limit, the lower limit here and the upper limit here. Y'all follow me? But this is infinite, which is nice. So that means this is going to be minus infinity to infinity. Now, I'm going to ask you this, just your gut. Give me your gut feel on this. Take a moment. How many people see for every charge I got here at a height z, I have conjugate charge here that would also have the same magnitude? It would be symmetrically located. And what does that tell me about the electric field in the z direction? Anyone? How many see it cancels? Right? Can you all see it? That one's going to have same exact magnitude, a direction that is exactly opposite in the z direction. This electric field component. This one's a minus, this is a plus. They'll annihilate each other. Now, you don't have to take my word for it. You can do the integration. You'll see, in fact, what I tell you is the truth. But what it does for me is it tells me that I don't need to do this integration, which I'm just pleased about, because I don't want to do it. The z integration you can forget about if it's infinite. Now that's just insight. Whitworth talks about, uses arguments of symmetry and stuff. Mathematically, you would get thrown out of the College of Math and Science if you did that. That doesn't work with them. You'd have to do a rigorous proof. But we're engineers, we want the answer. That's the answer. Okay? Come down to here. Now I'm left with this integral over here, right? What happens to this integration? My integration is dz. Does this look familiar? dz over rho squared plus z squared to the 3/2. Doesn't that look like the what? dx over x a squared plus x squared to the 3/2 integral we just did a second ago? As a matter of fact, it is. Let me give you the answer. You can look it up. The E field will only be in the radial direction, and after all is said and done, it'll be proportional to rho L. It'll be a 2 pi epsilon naught rho, and it will be in the a rho direction. That's the answer. Now that's the answer for an infinite line charge where the charge density doesn't vary. Now why that's such an important problem is this. There are many situations in life that look like an infinite line charge, approximately. I'll give you for instance. You see those power lines, right? Power lines, and just about anything that's got an insulator around it, and they do. They have some sort of, I think it's plastic these days, but I'm not actually sure. in insulation, it'll hold charge. Have you ever taken a balloon, rubbed it on your head and stuck it on the wall? Anybody ever done that kind of stuff? Static electricity, when even air currents moving over a power line will cause charge to be developed there. And I can't get into all the physical mechanisms right now, but it has to do with the fact it can't decay. Once it's there, it's gonna stick until something gets it off, so, because it decays so slow. So it'll be on there. Now, if I get real close to a power line, let's say this is a power line. If I'm this far away from something that's got that distance, it still doesn't look like it's infinitely long. But if I'm this far away from this thing, then it looks infinite to me. Can you buy that? So with a power line, if I'm real close, a couple of feet away, then I've got a pretty good, I could say that's approximately an infinite value. And if I can measure the electric field at a radial distance, I can back out what the charge density is if I needed that information. And sometimes it's valuable, sometimes it is. But that's where you see this type of information or this type of formula being so useful. It's approximating real world things when you're close to them and they look infinite. That's the reason why. So anyway, that's what it is for an infinite line charge. Now, for a problem, think about this. I could give you an inverse problem. I can say I have this long, very long very long line that's got a charge density on it. I want to know what it is. I'm out a distance 10 meters from it, and I give you the value of the electric field. Surely you can give me the value of rho L. Y'all with me? That's the kind of thing you have to be aware of. All right. Next problem is going to be a disk. We're going to get an electric field from a disk, and these are all classical problems. A disk with a certain surface charge density. I just want to go through these because some of these get irritating, but the way we do these problems, and I got to tell you, is we use what I call the building block approach. If we know the electric field from a loop, then we'll make the loop fat and get the electric field from not fat, with something with a little width to it on the z-axis, and then we'll just integrate that electric field over the range. Now, by this, what I'm talking about is I'm going to have this. All right, now I've got a disk. So disk means it's solid, right? I'm not going to show you what a solid is, but the disk right here is going to have a radius, as you might have guessed, A, and it's got a charge density here of rho S, and this is going to be assumed to be constant, but it doesn't have to be. Y'all follow me? It could be a function of the radial distance rho. And what I want to do is get the electric field at a point Z. Don't know what that is, at a height Z. So this height is going to be Z. So the way I do it is this. Now, I want you to all write that and just follow me on this one because it's important you see what I'm doing. I'm going to say, let's assume I have an actual inner loop of radius rho here. Y'all with me? And make rho a little bit, I call it fat, but give it some width. All right. And this loop is going to have a thickness of d rho, okay? Now, follow me on this. You know the electric field from a ring, right? I'm going to put it up. Remember, this is what I'm after. So I know the electric field on the z-axis from a ring would be equal to, I'll just write it down. This would be the differential electric field. Is normally rho L A Z over 2 epsilon naught A squared plus Z squared to the, and this is going to be 1/2 power, and be 3 halves power, my bad, 3 halves power. And it would be in the AZ direction. Are you with me on that? That's just, that if you have a loop, correct? We don't have a loop. We've got a ring that's got some width to it. And the charge density that I put on here, rho s, as the units of charge per meter squared. Well, actually, if I take rho s times d rho, that's equal to simply rho L. Y'all follow me? Take rho s times d rho. Now you get rid of the facts, you might say. You put all the charge on an infinitely thin strip. So I can replace rho L here. AZ twice. Or no, I don't. This is AZ unit vector. And now I can go ahead and put rho s d rho. And that would be the differential electric field in the z direction from this right here. And there's one caveat to this. Now, instead of A, my A becomes rho. Can you see this, class? Now the radial distance to this purple ring, right, somewhere inside of the outer radius. Now this becomes rho, and this becomes rho squared. Y'all follow me how I'm doing this? How many do? I'm trying to take a known value of a differential field. Well, I know what the field is for a loop, right? And what I want to do is just pound that into the form I need to do the integration. My only concern is now I have to take the constant radius A from the single loop and make it rho, because it's going to vary from the outer to the inner. And the differential charge then becomes simply d rho times rho s instead of rho L. Oh, now that's the differential field. If I wanted the total electric field from this loop, or from this disk, then I'd integrate from rho equals 0 to rho equal A. And that would be the total electric field. Are you with me on this, class? Right? When you do it, what happens? Well, in this case, I'm going to pull the constants out. I get rho s, z doesn't change, right? I get 2 epsilon naught out front. I can leave AZ here, and now I have the integral of rho d rho over rho squared plus z squared to the 3 halves power. And how do you want to do this one? Y'all realize that's a nice integral? Back in the day when you had integral calculus, these are the ones you live for on quizzes. Why? Because you got a rho d rho up here and you got a rho squared down here, so I know I can make this thing work in terms of an easy integral, right? How would you do it anyway? I got a minute, maybe.
Substitution.
All right, you're substituting. What would you sub? You want to make u squared or u equal to, make u squared might actually work. Okay, take a look. If you make u squared, you'll see what I'm up to. Equal rho squared plus z squared. Remember, z is a constant, right? Then you have to take a derivative of that on both sides. So I get 2u du is equal to 2 rho d rho, right? Correct, everyone? And the 2's go away, hopefully. So I have, remember, the limits are rho here. I'm going to change it down here. I've got rho d rho, that's u du here, right? And now I got u squared here, don't I? Y'all follow me what I'm up to? I'm not quite done here. My limits, rho equals 0. Well, when rho equals 0, u equals z, right? Or, yeah, z. Oops, sorry. When, you can get away with it, yeah. You would say, since I made this the truth, then you could say, this would be U equals Z, I'll explain the problem with them. If you take it and literally make, hold it. When rho is 0, yeah, U would be Z squared. So this would be Z, and then finally up here, how about I do it this way? I'll take the positive square root. Y'all with me? I just replaced the limits. Instead of having limits with rho, now they're limits with U. Follow me on this? Now, why is this a nice one? Just take a look. U squared to the 3/2 power is U cubed, right? U cubed divided into U is 1 over U squared, right? And what's that integration? Some people mess these up. Isn't that the integral of U to the minus 2 du? Right? And what is that? 1 over 1 minus 2, correct? And then it would be U minus 1. Isn't that right? So that's really minus 1 over U. So this whole thing becomes rho S Z over 2 epsilon naught AZ, and then you put the limits in, and you're going to get minus 1 over U, and I gotta switch the limits, so you're gonna have 1 over Z minus 1 over the square root of A squared plus Z squared. And that will be equal to the electric field. Now please just hold on before you run out of it. Give me 1 more minute of your time. Now this, I know it doesn't look all that exciting, all right, but here's a thing that drops out of this. Remember, this is a constant charge density, right? What if we made the radius of this disk go to infinity? What would it look like? It would look like an infinite plane. You all follow me on that, class? Now, if the plane goes to infinity, this is the important point. I look here, that means A goes to infinity here, right? Now just listen to me. If A goes to infinity, what happens to this term right here? It goes to 0. If that goes to 0, what do you think happens here? You see the Z's cancel, you get rho S over 2 epsilon naught. This is an important thing. I didn't get a chance to do it the way I really wanted to, but if you have an infinite plane, with a charge density rho S, like if this is where it is, then the electric field above that plane is nothing more than rho S over 2 epsilon naught, and it points in the normal direction. It always points away from it. So if it's below that plane, it's equal to minus rho S over 2 epsilon naught A normal. AN just is a normal vector, and that's the important thing. If you have an infinite plane of charge, your electric field is not a function of how far away you are from that at all, because it's an infinite amount of charge if you think about it. So no matter how high up, it still looks the same size. All right? I can look from 90 degrees to minus 90 degrees, and my horizon never changes. It always looks infinite. And that's how you get the electric field from an infinite plane from a finite disk. Now, I've learned about this thing, about doing these differential forms. People do not like to spend a lot of time doing integrations. They just don't. And they get irritated, right? Force yourself to do some of them. On the quiz on Friday, I'm not gonna ask you anything crazy, but I'm gonna ask you to do something where you give me the electric field from some of these canonical geometries, either lines or loops or disks, at 8 points that are reasonable. And I didn't get to say this, but everything here, you can use superposition. If you can get the electric field from one line charge at a point, and I put a second line charge from the total electric field, that same point is just the sum of the electric field from the first line charge plus the electric field from the second line charge at that point. All right, I'll give you a bunch of homework, some homework, and on Friday, I'll give you a quiz. Now, my quizzes are based on homework. By this time, it should be pretty clear. There's nothing coming out of left field, but you have to know how to do the homework well. Okay, see you then.